Hello, good morning. Spin-spin coupling. The source of signal splitting in NMR spectra is a phenomenon spin-spin coupling. The interaction spin of neighboring magnetic nuclei in a molecule is known as spin-spin coupling. The coupling occurs through the bonds by means of slight impairing of the bonding electrons. The complexity of multiplet depends upon the nature and number of nearby atoms. Chemically equivalent protons do not show spin-spin coupling due to interaction among themselves. That is, only the non-equivalent protons show the property of the coupling. Chemically equivalent protons do not show spin-spin coupling due to interaction among themselves. That is, only the non-equivalent protons show the property of coupling. Example 112 trichloroethane. H and Sp protons are spin coupled to each other, and therefore it has been observed that each kind of protons we cannot get singlet but groups of peaks are observed. Coupling may either oppose or reinforce the field felt by the other molecule. For example, ethyl bromide. In this molecule, the spin of the two protons CH2 methylene can couple with the adjacent methyl group CH3 in three different ways. Strongest field in the case of the fields due to the hydrogens cancel each other out. Weakest field in first case reinforcing, not affecting, and opposing. Account for the splitting of PMR signals or spin-spin coupling. We assume that one type of protons give rise to one signal or peak in the PMR spectrum. In actual practice, it is not so. Consider for the example of the following compounds. 112 tribromoethane, ethyl bromide, 11 dibromoethane. An examination of the above compounds reveals that each one of them contains two types of protons. We expect to observe, therefore, two signals in each case, but this is actually not the case. We observe that 112 tribromoethane gives 5 peaks, 11 dibromoethane gives 6 peaks, and ethyl bromide gives 7 peaks. This phenomenon of splitting of peaks into several peaks is called splitting signals. Splitting of signal takes place when there are non-equivalent protons on adjacent carbon atoms. Thus, in ethane, all the 6 protons are equivalent, hence no splitting is observed. Splitting of signals is explained on the basis of spin-spin coupling of the observing and neighboring protons. Let us consider a case of two adjacent carbon atoms carrying non-equivalent protons, one having two secondary protons and the other are tertiary protons. Secondary protons and tertiary protons. This is the secondary and this is the tertiary. Letter T and S for the tertiary and secondary respectively. Consider the observation of by one of the secondary protons magnetic field produced by neighboring proton, that is tertiary proton, may have two possible orientation with respect to applied magnetic field. If the magnetic field produced by the proton is oriented along the applied field, the secondary protons experience some increased magnetic field strength. Consequently, the secondary proton will observe at lower applied field downfield, than it would have done in the absence of tertiary protons. If the magnetic field produced by the proton is oriented against the applied field, the secondary protons experience some decreased magnetic field strength. Consequently, the secondary protons will observe at higher applied magnetic field than it would have done in the absence of tertiary protons. Considering that there is an equal probability of the tertiary proton magnetic field being aligned along or against the applied magnetic field, half of the secondary protons will observe downfield and other half will observe off-field. This one peak will be split into two peaks, doublet. Okay, sorry. With equal peaks intensities as shown below. Off-field, down-field, orientation of tertiary protons, applied field, single from a S proton, singlet secondary protons in the absence of tertiary proton. In the first case, the tertiary proton will observe downfield. In the second case, the tertiary proton will observe upfield. In the third case, the position of the signal will not change. As a result of above modification, the peaks due to tertiary proton will split into three peaks, triplet. The relative intensities are in the ratio 1:2:1. The central peak is of double intensity because it belongs to third case as given above, in which one proton is along and the other against the field. If we design it, the secondary proton as number 1 and 2, the proton 1 is along and the proton 2 is against the field of the proton 2 is along and proton 1 is against the field. The middle peak corresponds to case third, which takes into account both these possibilities, and the middle peak of the double density is dramatically shown below. Signal from tertiary proton in the absence of secondary proton, off-field and down-field orientation of secondary protons. Now consider the absorption of tertiary protons in the case of two neighboring secondary protons may have three probable combination of the spin alignments S1, is given below. Case first, the two protons are aligned with the applied magnetic field. Case second, the two protons are aligned against the applied magnetic field. Case third, the one proton is aligned along the field and other proton is aligned the field. Okay, it's all about spin-spin coupling. Thanks for watching and request you all like, comment, share, and subscribe. Thank you for patience. That's now bye bye. See you again.